Evelina.
Hello? Yes, ma'am.
Yeah, please start.
Hello?
Please start.
Ma'am, am I audible? Hello?
Please start now.
Hello? Okay. Okay. So, welcome back to the third lecture. Now, Professor Boyle is going to present. I welcome you, sir. So, before he starts, let me introduce. So, Professor Latham Boyle, he got his PhD from Princeton University and he has held a postdoctoral fellowship at the Canadian Institute for Theoretical Astrophysics, CITA, and a CIFAR Junior Fellowship. He has been a faculty member at the Perimeter Institute for Theoretical Physics since 2010. He is interested in a variety of different topics, including cosmology, particle physics, gravitational waves, black holes, and non-standard crystals, including the choreographic crystals and quasi-crystals. He has a number of publications in highly reputed journals like this Physical Review Letter, Physical Review B, etc. And so it's over to you, sir.
Okay, thank you so much. Well, thank you to Professor Dr. Mukhya and to Professor Biswajit Chakraborty for the invitation. I have to apologize that I haven't been able to attend most of the lectures because there's a 10.5-hour time difference between North America here, and so they're all taking place in the middle of the night for me. So, but anyway, I'm very glad to be here. So let's see, I guess I'm going to share my screen and try to do kind of a Blackboard type lecture. So let me see if I can get that to work. Okay. Can you see my screen? Can you still hear me?
Yes, sir. Yes, sir.
Oh, great. Okay. Okay, and so now you can see what I'm writing?
Yeah. It's clear.
Okay, great.
Yeah.
Thank you. Okay, yeah, so my name is Latham Boyle, and I'll be talking about, you know, I like the topic of this workshop, applications of group theory to, applications of group theory to other problems. That's been a very important theme for me. I sort of love that topic, and one of my favorite applications, the one that's maybe closest to my heart, is the application to understanding what the fundamental laws of nature are and what the fundamental theory of particle physics is, of the elementary particles and how they interact with one another. For my money, this is like the greatest puzzle there is. It's this sort of ongoing puzzle about what are the fundamental laws of nature, and people have been, humanity has been gradually making progress on this puzzle now for, maybe a couple thousand years, but really much more rapidly over the past few hundred years, and then much more rapidly over the past century. Then famously in the 1970s, the current standard model of particle physics was discovered. And that's sort of one of the great triumphs of 20th century physics. And it continues to do a spectacular job of describing experiments, laboratory experiments on Earth. It's less clear how much it can explain about the cosmological facts we see around us when we look out into the universe outside the solar system. So there seem to be some things out there that it's, maybe can, maybe cannot explain. There's actually some uncertainty about that. But so famously, there's dark matter and dark energy to be explained. And then also there are the special properties that we observe when we look back into the very early universe, which many people think are due to a period of so-called inflation. I happen to think otherwise, but anyway, I consider it not a settled issue exactly why the early universe had the very special properties we observe it to have. So, I thought I would introduce this topic. To me, this is a kind of ongoing puzzle that it's like there was the putting together of this giant puzzle. I think of it like a jigsaw puzzle, and at any moment in history, there are sort of a bunch of there's a part of the puzzle that's maybe been put together successfully in the middle of the table, but then surrounding it, there are some pieces which are clearly relevant, but no one has quite figured out exactly where they fit around the edge of the puzzle, or if they even connect to the current puzzle, or we'll have to wait a while for them to connect. And then occasionally experiment comes along and drops a few more new pieces onto the table that nobody expected. And then you get to make a bit more progress, hopefully. So, what I wanted to try to do was in lecture 1, I was going to sort of try to rapidly summarize the standard model, which is, give a sort of brief introduction to the standard model and the sort of fundamental role that symmetry plays there, which, if you want, is the part of the puzzle that's already been put together. And then the next 2 lectures will be more about how to extend the puzzle, how to get a deeper understanding of the standard model that we see, or what may come beyond it. And so let's see, maybe I'll move on to a new. So just in more detail. So lecture 1 will be about the standard model itself, an introduction. In lecture 2, I'll be talking about there was, for my money, the best clue that we have about that goes towards giving us a deeper understanding of the structure of the standard model than we currently have were these ideas that normally go under the name of grand unification from the 1970s. And there's kind of, so I'll tell you about those ideas, which really and in particular, there are parts of those ideas that really have to do with the topic of the course, which really have to do with this workshop, which really have to do with thinking hard about the symmetries of the standard model and the representations of those symmetries that are used in the standard model, and then how those relate to certain larger symmetry groups and their representations. And that's the part of grand unification that is both most relevant to us, and also the part that really works the best. I mean, that's the most successful. So anyway, that's what I'll be talking about in lecture 2. There's other ideas that go under the heading of grand unification, which, well, it's less clear whether they are right or not. Experiment hasn't been kind to some of those other aspects of grand unification. But anyway, so I'll be talking about the relation of the standard model gauge group and its representation to the groups SU5 and SO10, which are sort of the 2 most beautiful cases. And then there's another related case, grand unification scheme called Patty Salam, which has to do with the group SU4 times SU2 times SU2, which we'll also meet briefly. Okay, and so that's a sort of again, for my money, that's the best clue we've gotten so far about sort of a deeper understanding of the standard model or what comes beyond it. That's pretty old. That was discovered right after the standard model itself in the 1970s. In lecture 3, I want to introduce something more recent, which I think is I think of as maybe the other best clue that we now have, although it's much less well known. So this was in 2018. Bulgarian physicist and mathematician Ivan Todorov, who was once upon a time was back in the 60s and 70s was one of the fathers of axiomatic field theory and the conformal bootstrap. But he, like a handful of us, have been thinking about the possible relationship between the standard model and a very special mathematical structure called the exceptional Jordan algebra. I also had been thinking about this, but never quite got it to work. And so he made what I consider to be a breakthrough on that topic back 2 years ago. And so then I'll try to introduce that to you and some of the related ideas and a follow-up paper that I wrote about that this past summer. So that's about, yeah, that also relates it to other topics, which are very, very beautiful and interesting topics, I think. The so-called magic square of Lie algebras and triality. Okay, so that's the plan. So let's see. Maybe I'll start another page. By the way, I should mention just that I've tried to not overload the lectures with too much information. I'm going to be giving exercises here and there to try to not required exercises, but just suggested ones that I think would be useful if you were interested. But in an effort to not make the lectures too packed, so that there's plenty of time for questions. So I should just want to encourage you, if anyone wants to ask questions either now or there should be time left at the end, that please feel free. Okay, so let's see. So I know that in the course you've been learning about groups and symmetries, and a basic division is that groups can be either discrete or continuous. So in other words, they can be divided into symmetries that are sort of discretely separated from one another, and maybe even a finite number of those. And so my favorite example, well, one of my favorite examples of a discrete group is based on, one of my favorite shapes in 3 dimensions, the icosahedron, which is, one of these 5 Platonic solids where you allow 5, let's see if I can do this. Sorry, I thought this would be not so difficult. Normally, if I'm drawing with a pencil, in my mind, this was something I was just going to quickly sketch and then refer to, but then with this tablet, I'm not that good at drawing. So, okay, so I don't know if you can even see this now, but so this is supposed to be, an icosahedron. Most of you are probably familiar with it, but it's this 20-sided shape where every side is an equilateral triangle and 5 of them meet at each vertex. Very beautiful shape. And so this is an example of an object that has a discrete symmetry group. There's 120 different ways that you can either rotate or reflect this object so that it ends up getting carried back into itself and looking just like it did before. On the other hand, if you have a sphere, that's an example of an object with a continuous symmetry group, because now you can choose any axis you want going through the sphere and rotate by any angle you want around that axis any axis going through the center of the sphere, of course, and rotate by any axis, any angle you want around that, and that's still a symmetry. So that's a continuous symmetry group. And so continuous groups here, what we're talking about are so-called Lie groups, more specifically. So these are this is the case where the group itself can be thought of as a manifold, like this, like the surface of this donut that I've drawn, and where the idea is that now any point on this manifold is itself actually a member of the group, is an element of the group. So yeah, they form a smooth continuous manifold. Fine. And so the symmetries that come up in this standard model are, well, most of them are of this type. So in particular, the space-time symmetry is the Poincare group, or in flat space. Oh, I should say. So let's see. So we have sort of 4 fundamental forces of nature: gravity, and then 3 more. So there's the strong, weak, and electromagnetic force. In this lecture, I'm going to leave gravity aside for the time being, for the sake of trying to get through the standard model more easily, and then we can come back to gravity later. But so in this lecture, yeah, I'll be focusing on just the standard model of particle physics, which really describes these remaining 3 forces. And so living on a flat Minkowski spacetime. And so the relevant symmetries then are the Poincare group, which is an example of a Lie group. And in particular, important subgroup of the Poincare group is the Lorentz group, SO3, 1, which you learn about in special relativity. And then, fine, those are the space-time symmetries, but then there are also the internal symmetries in the model. So these are symmetries of the action, but they're symmetries that act by taking the different fields in the theory and mixing them up with one another without acting on space-time. So they don't translate you or rotate you or boost you in space-time. They just act on the fields themselves internally. And so there we have a different Lie group, which ends up being relevant: SU3 times SU2 times U1. Okay, yeah. And moreover, the groups that appear in physics, they turn out to be gauge groups. So in addition to being continuous groups themselves, you have a freedom to choose an element of this group over every point in space-time. You can choose a different element of this group, SU3 times SU2 times U1, over every element of over every point in space-time, and still that huge collection of different group elements will provide a symmetry of the action of the standard model of particle physics. Okay, so let's see. There's one other thing which I wanted to mention, which I should have mentioned at the outset, but just realized I glanced over in my notes, which is just that, okay, for the sake of time, since the idea is to try to get to, I wanted to. The point of these lectures is to sort of present this puzzle so that you can, to at least give a glimpse of what I think of as one of the most interesting sort of edges of the puzzle, or something like that, where the forefront, where maybe some progress is being made. And so the idea, was to, as I mentioned, was to first introduce the standard model itself, and then so that we at least know what we're talking about a little bit, and then and then get to ideas about how to extend the puzzle. But you know, of course, to do that all in 3 lectures, it's a short time for a rather big topic, and so it'll, by necessity, the lectures will be, I mean, I'm hoping that they'll be as clear as possible, but by necessity they'll be a little bit sketchy at points, and especially if you know, have no background in this topic, it will be fast. So I just wanted to mention that I'm also teaching a more extended version of this. I'll be teaching in the winter and spring at the Perimeter Institute, where I work, a course for master's students, which is sort of a more a longer, more pedagogical, more thorough introduction. The first half to the standard model, and then the second half to sort of a review of an introduction to some of the most important ideas about physics beyond the standard model, or deeper ideas about the standard model. And so yeah, so that'll be a sort of more extended introduction to all of these ideas. And I'll be trying, since this year we're having to do the lectures over video, I'm planning to record those and hopefully post them to YouTube. So if you're interested in a more detailed version of that, those should be available in a few months. And if you can't find them, let me know and I can send you the links. Let's see. Okay, so now let's get, the idea now is to begin to say what the standard model is in more detail, more mathematically. So, you know, the standard model is an example of a so-called Yang-Mills theory. Also known as a gauge theory. And so we want to explain, you know, what's the basic idea? What is Yang-Mills theory all about? And then, so first I just want to give the sort of physicist's introduction to what Yang-Mills theory is in general, and then the standard model is a particular. So the standard model is a specific. So from now on, let me call this Yang-Mills theory, YM. So the standard model is a specific Yang-Mills theory. So first we'll discuss what Yang-Mills theory is in general, and then how to specify the standard model in particular. And we'll end up with the Lagrangian, or the action formula, which defines the standard model. Okay, so what's the idea in Yang-Mills theory? So let's say this is so space-time is some manifold here. I'm just going to draw so space-time is some manifold like this. Now, to define, so Yang-Mills theory is a field theory over space-time. It's a generalization of electromagnetism. And to define it, well, we have to start from the right concepts. So the way Yang-Mills theory will work is that to define a particular Yang-Mills theory, before I tell you what Yang-Mills theory is, let's sort of give the algorithm for how we'll define it. So we start, Step one is we pick a Lie group, G. which is going to be the basic gauge group of our theory. So in the case of the standard model, this would be SU3 times SU2 times U1. But for now, we're just going to let G be some more general group. Maybe just for concreteness, we could even, for simplicity, we could even imagine that it's at the beginning, when you're just getting started, it might be easier to imagine a simpler group like SUN with just a single component. Okay, so then step 2, after we pick our group G, is that we're going to pick a representation of G. So a representation rho of the group G. So the representation is a map from which takes any element little g of the group, so for any element G in our group big G, the representation is a map from that element to an n by n matrix here. And that map has to respect the product in the group G. So the requirement is that the map carries the product G1, G2 to the product of the corresponding matrices, rho of G1 times rho of G2. Where here we have the product in the group, but down here we have the product of the corresponding matrices, the ordinary matrix product of rho of G1 and rho of G2. Okay, and if the map rho, if the representation is a map from the group element to a set of n by n matrices, then we say this is an n-dimensional representation of G. So a given group G can have many different representations of many different dimensions. So for example, for SU2, there's also there are irreducible representations with one dimension, the trivial representation. There's also a representation with 2 dimensions called the fundamental. But then there's also a 3-dimensional representation, 4-dimensional representation, etc. Okay. So now I lost my picture, so just to have this to point at, let me just draw it again. So now the idea is that this n by n matrix rho of G acts on some n-dimensional vector space, and so let's say it acts on V, which is an n-dimensional vector space. So the idea is that, so this is some vector space, and we'll imagine that we have a copy of this vector space living above each point in space-time. So at each point in space-time, we're going to have a copy of this vector space living there. So we have one copy of V living over that point, but then we have another copy over this point. We have a copy of V living over every point. And so a vector in this vector space will be some vector psi. And if it's a vector in the vector space living over the point labeled by the coordinate, if this is the point on space-time labeled by the coordinate x, we'll call the vector living in this space psi of x. And if it's the vector living in this vector, for this point over here, labeled by a different coordinate x prime, we'll call that guy psi of x prime. Okay, so all of these vector spaces together make up a so-called vector bundle living over space-time. And the function psi of x, where now x runs over all space-time coordinates, is called a section of that vector bundle. Okay, just a choice of a particular vector in each vector space over the space-time. And so these, in Yang-Mills theory, this is what the matter fields will be. They will be sections of the matter fields in a Yang-Mills theory are sections of an n-dimensional vector bundle on which the n-dimensional representation of G will act. Okay, so just to be a little more concrete, so suppose we have a matter field psi of x, and it lives in that n-dimensional vector space, and we also have chosen an n-dimensional representation of our group G. Then previously I was calling the n by n matrix rho of G, but now to be a little bit more brief, why don't I just call that, and also to remind myself that I'm thinking of this example, this simple example where the group is SUN. I'll call this matrix U in what follows. Okay, so in other words, for an element G of my group now gets mapped to an element U of G instead of rho of G. I realized I switched notation in my notes, and I want to warn you ahead of time that I'm calling it U of G now instead of rho of G, because otherwise I'll forget and do it anyway. So our matter field psi of x, it can then naturally transform. The gauge group has a natural way of acting on it, which is that it can send psi of x to a new, it can transform it into psi prime of x, which is defined to be u of x times psi of x. So is that clear? So the idea here is that I started with this section of my n-dimensional vector bundle. So in every vector space living over, in the vector space living over each point in space-time, I start with a choice of some vector. And then the idea is that it's going to transform to a new vector, psi prime, by, well, at each point, I can freely choose a different element G. So I can choose a different element G of my group capital G above each point in space-time. And then each of those G's gets mapped by the representation to an n by n matrix, U, corresponding U. And that U acts on my original vector, psi, to give me my new vector, psi prime. Okay, is it does that maybe I should pause. Do people understand what I'm talking about or no? Does anyone have any questions about that?
I had a question.
Yes, go ahead.
Earlier you mentioned that the dimensionality of the space of the dimensionality of the representation
Yes.
is the same as the dimensionality of the group G. And later, since the representation acts on the vector bundle, that also has the same dimensionality. Is there any reason for this specifically?
Let me see. So it's not that the dimension of the vector here, the vector psi, has the same dimension as the dimension of the group. The dimension of the group is a different thing, but it has the same dimension as the dimension of the representation of the group. And these are just it's just the structure of it's the logic of how a Yang-Mills theory is constructed is that you, as I say, one, you choose G. Then two, you choose a representation of G, which has some dimension. So in particular, you choose an n-dimensional representation of G, where n is part of the choice. And then you let a copy of that representation live above each point in space-time. So that representation naturally acts on an n-dimensional vector space. So you have you let this representation so again, if we call our representation rho, we now let rho act on a vector space V living above each point in space-time. And so since we chose a rho which was n-dimensional, which consisted of n by n matrices, to make sense, we should be also choosing a vector space V above each point in space-time, which also has that same dimension n. Is that clear?
Yeah, that's clear. Thank you.
Okay. Anything else? Should I go on? Why don't I go on? Okay. So great. Now the whole idea is that in Yang-Mills theory, so fine, I have my matter fields, psi of x, or let me just suppress the of x now. I'll just so I have my matter field psi. And so suppose I wanted to write down now the goal is I want to write down an action, some function of psi or functional of psi, which is invariant under this transformation. So I want it to be the case that when I take psi goes to u of psi, the above transformation, that the action doesn't change. That s of psi goes to s of u of psi, but that's just equal to the goal. We're trying to construct a theory which has the transformation as a symmetry, so that should just be equal to s of psi. Now the problem is the problem which still remains to be solved is that this Lagrangian, it's not just going to depend on psi. In a physical theory, it's going to have to also depend on derivatives of psi. D mu of psi, like a derivative with respect to space-time. So d mu of psi is my shorthand notation for the partial derivative of psi with respect to the space-time coordinate x mu. So in practice, Lagrangians have fields have kinetic energy terms, which depend on the derivatives of the fields. And so if we don't have any derivatives in our Lagrangian, we're not going to have any dynamics going on. So the actual physical theories in nature, we're going to need derivatives of the fields. And the problem is that, okay, we chose this nice transformation law for psi, but now when we take the derivative of psi, this thing no longer transforms nicely. It transforms to d mu of u of psi. But then because of the Leibniz rule, when we expand that out, we get, two terms. We get one term like that and a second term like that. And if we had just gotten this term, we would say that this guy transforms tensorially, just like this one does. It has a nice. It would be saying that if d mu psi just transformed to u d mu psi, it would transform linearly, just like the original vector psi did, and we'd be able to construct a nice invariant action from this object. But instead, we have this extra term, which is spoiling things, messing up the transformation law. And so that'll give us trouble when if we try to write down a function, an invariant function involving this thing. That will get in our way, that extra term. So we need to fix that problem somehow. And so the famous fix is invented by Yang and Mills, is just a generalization of what happens in electromagnetism, which is that we replace the partial derivative by a covariant derivative, which consists of the partial derivative, but then plus Ig times the electromagnetic gauge potential, or more generally, this is the A mu is now, in electromagnetism, this would just be the electric charge, and this would be the electromagnetic 4 potential. But now this is the Yang-Mills. This will be called the Yang-Mills coupling strength, and this field will be called the Yang-Mills field, or the gauge field. So the idea will be that so now instead of taking the partial derivative of psi, we'll take the covariant derivative, capital D mu of psi. And now we want this thing to transform nicely. We want it to be the case that the transformed d mu of psi transforms just like psi itself. Okay, so we want d mu of psi all primed to just be equal to u of the original d mu of psi. And so you can see that would happen. And we want to take that assumption and figure out thereby how the Yang-Mills field has to transform. So you can see that, well, oops. So if we expand this out, d mu, this is d mu prime times psi prime, but then psi prime we know is u psi. And so d mu prime, if we want it to transform properly, d mu prime should be u d mu. I should have written that bigger, sorry. My skills with this program are not so good. Okay, so so we know that psi prime transforms to u psi. That's our starting assumption. And so in order to get the whole product to transform like this, we see that what we want d mu prime to transform to is u times d mu times u inverse. Because then this u inverse will cancel this u, and we'll just, and this expression will simplify to u d mu psi, which is what we want. Okay, so in other words, we want our covariant derivative to transform like u goes to u d mu. Sorry, it goes like d mu goes to u d mu to u inverse. And then so we can check if we just substitute in our expression for the covariant derivative, d mu plus I g a mu over here. And in fact, let me write this slightly differently. So we know that we want d mu prime to be equal to u d mu u inverse. And so if we rewrite d mu prime as d mu as partial mu ig a mu prime, and then we rewrite the other side as u times d mu plus I g a mu u inverse, then if we just simplify this a little bit, we'll find the rule for how a mu has to transform. A mu has to transform, in order to make this equation true, a mu has to transform to a mu prime is equal to u a mu u inverse minus I over g u d mu u. Okay, so that I'll leave that as an exercise to check. It's a simple exercise, but worth checking. So that's how you figure out how a Yang-Mills field has to transform. In
Latham, it should be del mu u inverse in the second term.
There's equivalent. This is equal to. That's a good point. Let me extend the exercise. This expression is actually right, I believe, but then there's a second term here. There's a second expression which is equivalent, which is plus I over g times d mu u times u inverse.
No, but then the first term will be, because one of the u's should be u inverse.
Oh, yes. I'm sorry. Oh, yes. Oh, sorry. I didn't understand the comment. Yes, you're absolutely right. Thank you. Thank you very much. So this should be u inverse here. Thank you. Yes. Thanks for pointing that out. Okay. So great. So now we find that sort of inevitably in addition to the original matter field psi that we originally thought we had in the theory, we originally thought we were going to build our action from psi, but now we've been forced to include another type of field, this term a mu, which geometrically represents a connection connecting the different vectors, these different n-dimensional vector spaces in our n-dimensional vector bundle. But then physically is what we will end up interpreting as the field that carries the Yang-Mills force between these matter fields. So it will end up mediating a force. And so this field A mu is the Yang-Mills generalization of the photon, or of the electromagnetic gauge potential. Okay. So to go a bit further, great. So we have defined our covariant derivative d mu. Now we're used to the fact that if we take the commutator of two partial derivatives and act it on something, So for example, so this is d mu d nu minus d nu d mu. If we take the partial derivative in the x direction and then in the y direction, minus the partial derivative in the y direction and then in the x direction, for normal partial derivatives, they commute. And so that would be 0. But now when we do the same thing with the covariant derivative, this is if you want exercise 2. If you just check the same thing, you take the commutator of 2 covariant derivatives. Then this is not equal to 0 anymore. Instead, you can check that it's equal to something times psi. Okay, and this something we will call Ig times F mu nu, where F mu nu, this is the definition. This equation can be taken as the definition of the Yang-Mills field strength. And so this is the generalization of the electromagnetic field strength. And you can check that it is given, if you just work out this expression, you work out both sides of this expression, you'll find that that the Yang-Mills field strength is given by a piece that looks just like the ordinary expression from electromagnetism. And then a third, this commutator term, which is new, which is you don't get in electromagnetism. Okay, and now you can furthermore check. So exercise 2 is, I guess, would be to just derive that, and then exercise 3 is you can check that A mu, remember we were going to all this trouble. To, we had trouble that d mu of psi wasn't transforming right. There was sort of an extra term spoiling the transformation law. And so we introduced our covariant derivative so that now it transformed beautifully simply. But we paid a price, which is that we introduced an extra field, A mu, which doesn't transform simply. We said that it transforms with, there was a first term, which was nice and simple and would have been tensorial. But then there's a second term here, which was like, which was like this, and so which again seems to spoil the transformation law. And so again, we would, if we were trying to write down an action involving A mu, it would seem that we would run into trouble. How are we going to write down a kinetic term for this field? And well, so now F mu provides the answer. The answer is provided in equation 3 here, which is that F mu nu, I should say, F mu nu, you can check if you use this transformation law and you plug it into this expression for F mu nu, you can find how F mu nu transforms. And F mu nu does transform very simply. It just transforms to U F mu nu U inverse. So although A mu, the original gauge field, does not transform tensorially, its field strength, F mu nu, does transform tensorially. By the way, I should just add that F mu nu, physicists will call that the field strength of the gauge field A mu. But again, as I mentioned, there's a mathematician might say that A mu defines the connection on the on the n-dimensional vector bundle of the matter fields, and then they would say that F mu nu is nothing but the curvature of that connection up to a factor of Ig. Okay, great. So because F mu nu transforms so simply, we can write down, I'll start a new page. because f mu nu transforms so simply, we can write down the first term in our Yang-Mills Lagrangian now, which is that, well, we want to write down a term which is invariant under all of the desired symmetries of our action. So we want it to be, first of all, we want it to be Lorentz invariant to satisfy special relativity. And we want it to be gauge invariant. Meaning that when we do the transformation law involving these matrices U that we've been talking about, that the action is invariant. Well, but we can write down such a term involving f mu nu. So first of all, to make it Lorentz invariant, we have to contract up all of the Lorentz indices. It has to be a Lorentz scalar, so it shouldn't have any indices hanging around. So we could try something simple here, like contracting maybe f mu nu with the metric eta mu nu, but that will give 0 because the metric is symmetric in its two indices, and the f mu nu, if you check from our previous expression, is anti-symmetric in its two indices. So that would just be equal to 0. So that won't work. So the simplest thing, it ends up be, if you think about it, the simplest way to get a non-zero answer for a Lorentz invariant quantity is to contract it like this, is to contract the indices like this. So now we have an object that's Lorentz invariant, and now if we ask, how does this thing transform under gauge symmetry? Well, it would transform, both of the f's would transform to u f u inverse. So we would get u f mu nu u inverse from the first factor, and then we would get u f mu nu u inverse from the second factor. And so these u's in the middle would cancel. U inverse in the middle would cancel, but we still would have a hanging u and u inverse on the outside. So we're not there yet, but we can fix that by taking the trace of this object. Okay, and now since the trace is invariant under cyclic permutations, we can bring this u inverse around to the front where it cancels the u. And so actually this guy, works. It's invariant under both Lorentz transformations and under gauge transformations. And so in particular, with the correct coefficient, with the normal convention, or one of the standard conventions, minus one quarter trace of f mu nu would be an example of a term we could write down in a gauge invariant action, gauge invariant and Lorentz invariant action involving the gauge field, and that is exactly what the kinetic energy, the kinetic term for a gauge field looks like. Okay, so what other sorts of terms could we write down? Well, if our matter field, so far I've just been referring to the matter field as psi. Let me now distinguish between, I haven't been paying any attention so far to how the field transforms under space-time symmetries, what representation it lives in of the Lorentz group. But now let's distinguish. One important type of matter field is a scalar field, which doesn't transform under Lorentz transformations. It transforms trivially. It has no indices. So I'll call the scalar fields now phi, and then I'll reserve psi. Maybe I'll call it capital psi. Those psi will now be spinor fields, meaning that they transform under the so this technically this transforms under the 0, 0 representation, the spin 0 representation of the Lorentz group, whereas these spinor fields transform under either the 1/2 0 or the 0 1/2 representation of the Lorentz group, the spin 1/2 representation. So for the scalar fields, well, we could just take now that we can form a nice covariant derivative of that scalar field, which transforms, which would transform like d mu psi goes to u d mu psi. Sorry, phi. So that means we can form an invariant here by taking a term like this. So here I've contracted this Lorentz index with this Lorentz index, so it's a scalar under Lorentz transformations. But also, when I take a gauge transformation, I get a u. This term picks up a u, but this term also picks up a u, but then we take a dagger, so we get a u dagger here. And this would be an example of a term that would be invariant if we were working with a unitary, if the gauge group was a unitary group. That's an important point, which I forgot to mention, is that exactly what terms you can write down in a Yang-Mills theory, which are invariants, depend on exactly what group you take and exactly what representations you take. So in this case, where I'm taking, where I was considering as an example the case where G was SUN, and so an element of that group was a unitary matrix U satisfying the property that U dagger is equal to U inverse. Then, if I look at this term, this U dagger is really a U inverse, and so it kills this U, and so this term is invariant. And so this is exactly what the kinetic term for the maybe with a minus sign depending on your conventions. This is what the kinetic term for the scalar field will look like. And then for a fermion field, there the kinetic term was discovered by Dirac. I won't describe it in detail, except to say that now we take our covariant derivative d mu, we contract it with these so-called Dirac gamma matrices, which I will have more to say about later in the talk, but don't want to introduce right at the moment. So this is that this thing now, Dirac discovered that that using spinor fields you could write down an object like this and it would be Lorentz invariant. But now by using the covariant derivative instead of Dirac's original partial derivative, we have also made it gauge invariant. Okay, so fine. So we have three types of fields in the standard model of particle physics. There's scalar fields, which are spin zero, represent spin zero particles, and spinor fields. So the scalar fields were our capital phi's here, and then we have spinor fields like our capital psi's, which represent spin 1/2 particles. And then we have gauge fields, Yang-Mills fields, which are sometimes called vector fields, vector bosons. And these represent spin zero particles. And now we've seen how to write down Lorentz invariant, gauge invariant kinetic terms for all three of those fields. And those are exactly what the kinetic terms in the standard model look like. And then, well, you could ask what other terms, so what, yeah, I mean, when a field theorist says kinetic terms, they just mean any terms that you write down in the Lagrangian or the action that do involve space-time derivatives, as these terms do, space-time derivatives of the fields. Then you could ask, well, are there other terms that you could write down that don't involve derivatives? And again, depending on exactly what gauge group and what representation you're using and what dimension of space-time you're working in, you can find other examples. So for example, with our scalar field, we might be able to write down a term like this, phi dagger phi, that since now when this transforms, get a u from here and a u dagger from here, which will cancel. So we could write down a term like m squared phi dagger phi, which would be called the mass term for phi. We could write down a term like we could take that phi dagger phi, which is already invariant, and now once we have a nice invariant, we could square it. That would be another example of another term in the potential for the scalar field phi. Or another important type of term we can sometimes write down, which is sometimes invariant, is a term involving one copy of the scalar field and two fermion fields. And that would be called a Yukawa term. And those also play an important role in the standard model. And so those are all the types of terms actually that appear in the standard model Lagrangian. And so that's my brief sketch of how Yang-Mills theory, of the logical structure of Yang-Mills theory and what it's about. And now I just want to end up by describing the particular Yang-Mills theory that experiments have told us describes our actual universe for some reason. And that's the standard model of particle physics. And that's really what we want to understand. So let's get to that. Well, maybe I should pause and just ask explicitly, are there any questions that anyone was wondering about? Anything confusing? What about the pace? Is the pace, how is the level? Is it right or too fast or too slow, or any suggestions in that regard?
So can I see you something?
Yes,
It's fantastic, sir. But there's one problem. Would you give some highlight on the molecular structures and all? Is it possible? I don't know. You are from a different field, but the presentation is fantastic. Actually, we're liking it. But time is limited. Even other teachers did the same thing, but time is limited. So in case, would you give some highlight on the molecular structures, the physical aspects of the mathematical expressions? That would help us whether time permits it.
Okay. So sounds good. So maybe this next page will be helpful in that regard. You know, so far I've been describing the formalism for how to write down, you know, so the laws of the standard model of particle physics, the sort of fundamental laws of nature as we currently understand them, are described by a field theory, and that field theory, the different dynamical variables in it are these different fields which represent different constituents of matter, scalar fields and spinor fields and vector fields, and the theory is defined by some expression, the action functional, which depends on these fields and is invariant under all of the symmetries we've been describing, and so that's the integral of some corresponding Lagrangian. But then physically, what does that represent, and how does it relate to the molecular structures that you see in a chemistry lab, for example? Well, because of quantum mechanics, this field theory is really a quantum field theory. You quantize it. You have to apply the formalism of quantum mechanics to it. And when you do that, each of these fields ends up describing ends up describing the elementary particles of nature. So the quanta of these fields are the elementary particles of nature, where by elementary here, I mean that as far as we know, so far, these particles cannot be divided into smaller bits. So these are the most fundamental constituents in that sense, that as far as we know, they are indivisible. And so the modern way of describing the standard model of particle physics is in terms of what are the indivisible elementary particles of nature and how do they get transformed into one another by these various symmetries. Now, if you look at an atom, you know, and sorry, I lost my pen here for a second. So you know, an atom has some nucleus consisting of neutrons and protons, and then it's surrounded by, okay, in my cartoon sketch, it's surrounded by electrons. So this electron will be one of the fundamental particles in the standard model. As far as we know so far, the electron is an indivisible particle. So it will be described by one of these spinor fields. I'll describe that more in a moment. But one of the spinor fields that appears in the standard model is the electron field, which creates and annihilates electrons. The neutrons and protons are also spin 1/2 particles, but they do not appear directly in the standard model because they are not elementary particles. So a neutron, roughly speaking, and a proton, roughly speaking, they're each made of 3 quarks. So a proton is made of 2 up quarks and a down quark, roughly speaking, and a neutron is made of 1 up quark and 2 down quarks, roughly speaking. And these quark fields, U and D, these quark particles, are, as far as we know, indivisible. So the up quark field and the down quark field will appear in the standard model Lagrangian. They will be other examples of these spinor fields that appear. So, and then of course, any larger molecules will just be made up of a bunch of atoms like this. So they'll be even less, you know. Anyway, so hopefully that clarifies a little bit how the fields that appear in the standard model Lagrangian, which describe the elementary indivisible particles, relate to the atoms and molecules that one is more familiar with.
Yes, sir. Thank you so much.
And so let's now get to the standard. Let's now get to the. So to finish up, I just wanted to get to the actual honest to God standard model. So let's do that now. So again, remember that the 2 steps that we needed, so far we've talked about Yang-Mills theory in general, but the 2 steps that we need to specify a particular Yang-Mills theory is, instead of dealing with a general group G, we want to pick a particular G, pick a Lie group G. Okay, so for the standard model, we're going to pick G to be SU3 times SU2 times U1. Why? Who knows? That's something that is still unsolved, and that the attempt to explain that is part of what lectures 2 and 3 will be about. But anyway, that's what. But based on experiments, we know that the Lie group G that is appropriate for the standard model is this one, SU3 times SU2 times U1. And now we're going to pick a now the next thing is we need to pick a representation of G. And so that is nicely summarized. What representation are we going to pick? Well, we're going to pick the one that is determined by experiment. And again, why does the universe use that particular representation? again, nobody knows. That's one of the great still unsolved mysteries of science, is where does this group and where does this representation come from? But experiments have at least told us what the representation is. And so let me tell you what that is. It's summarized in a little table, which for me is like a, you know, it's like a holy table. You know, it distills down into a little table. Essentially all we currently know about the fundamental laws of nature. So here along the top here, I'll write the three components of the gauge group: SU3 times SU2 times U1. And then each row represents a different irreducible representation of that group, and hence a different type of elementary particle in the standard model. Okay, so what are the different irreducible representations which appear in the standard model? Well, there's the left-handed quark doublet, which consists of two parts: the left-handed up quark and the left-handed down quark. And then, so that the left-handed up and down quark are in a single row, but the corresponding right-handed guys get their own rows. So there's the right-handed up quark and the right-handed down quark, transform in different irreducible representations. Okay, so those are the three quark rows, and then there's three lepton rows. So consisting of the left-handed lepton doublet, which again has two parts: the left-handed neutrino and the left-handed electron, and then the corresponding right-handed fields, the right-handed neutrino and the right-handed electron. Okay, and so those six rows define the different types of fermion fields that appear in the standard model, the different types of spinor fields, what I was calling capital psi before. And then we still have to say what types of scalar fields appear in the standard model. And well, again, who knows why, but experiments seem to say that there is only one scalar field in the standard model that we know of so far, which is the so-called Higgs doublet. And so now to fill in the table, well, what I'm writing here, what I'm filling in the first two columns of this table are the dimensions of the representations of SU3 and SU2. So the way it works, and again, we know all of this stuff from experiment. We don't know fundamentally why any of the entries of this table are what they are, but we know experimentally what they are. The quarks are the three spinor fields that transform as three-dimensional representations of SU3. Everybody else, the three lepton fields and the Higgs field, transform as one-dimensional representations of SU3. By the way, the one-dimensional representation of SU3 is the trivial representation. In other words, what this is really saying is that the lepton, these last three fields and the Higgs field do not transform under SU3. So only the three quark fields at the top transform under SU3. Under SU2, the left-handed fields transform in the two-dimensional representation of SU2, and so does the Higgs field. Whereas all of the right-handed fields transform in the trivial representation, the one-dimensional representation. In other words, they don't transform under SU2. And then the notation in the final column for U1 is a little bit different because the U1 is more analogous to electric charge. And so here what we're really giving are it's not the actual electric charges of these particles, because this U1 is something different. It's called hypercharge. So these are the hypercharges of the elementary particles. So that the hypercharge of the quark is 1/6, and then it's 2/3 for the up quark, minus 1/3 for the down quark, minus 1/2 for the lepton doublet, 0 for the neutrino, and minus 1 for the electron. and 1/2 for the Higgs particle. Okay, so as I said, the names are that the top 3 rows of particles here are called quarks. The next 3 rows, the other 3 fermions, are called leptons. This bottom field is called the Higgs doublet. And then associated with each of these different components of the gauge group up here is a corresponding gauge field at the top. So associated with SU3, we have the SU3 gauge field G mu, which is the field that physically causes or communicates the strong force. Associated with SU2, we have the weak Yang-Mills field W mu, which is the field that causes or mediates the weak force, and then associated with U1, we have a gauge field called B mu, which is the hypercharge gauge field, and together these gauge fields cause the so-called electroweak force. So B mu is not the photon, it's not the electromagnetic field, but a certain combination of B mu and W will ultimately leads to the electromagnetic field that one is familiar with. That's after a process called spontaneous symmetry breaking, which I don't have a chance to get into in this lecture. But so let's see. So in a final well, let's see. I guess I'm close enough to the end that maybe I should leave this to next time. I was just going to end by finally that we had all the ingredients in place to actually write down and look at the Lagrangian, or the action for the standard model of particle physics. But let me leave that for next time, since I see I'm running into the end of my time. So there you go. That's but the point is that this table, once I've given you this table, the rule for writing down the standard model of particle physics is that I've told you in this table all the fields that you have to use and how they transform under the gauge group. And now the standard model of particle physics is just the most general formula you can write down using these ingredients that is invariant under both Lorentz invariance and under all of these symmetries, SU3 times SU2 times U1. And when you try to write that down, you find there's a bunch of terms. There's a bunch of undetermined real coefficients that can appear in the expression, and which we don't know how to predict and are only determined from experiment. And so we're left with some basic questions which are unanswered at the moment. I want to emphasize these are sort of unsolved puzzles in physics, very basic. Why is the symmetry group of nature SU3 times SU2 times U1? There are an infinite number of symmetry groups to choose from. Why did nature choose this one? Why is the representation given by this bizarre table? There are an infinite number of representations that the particles of nature could have transformed in. And for some reason, we got this weird one. Where did that come from? It's not as complicated as it could be. It's not as simple as it could be. It's somewhere in between. It seems strange, but then as you begin to look closer, there's clear patterns there. We would like to explain where that's coming from. A third mystery, which is unexplained, which I didn't have a chance to mention, is that I actually showed here just one generation of the standard model fermions. For some reason, there are 3 copies of this. Actually, there's for each of the fermions I showed in the table, there's actually 3 copies. And so this exact pattern of this part of the table is repeated 3 times. Why? Where is that? What is that about? Why 3 generations? It's an obvious obvious puzzle nature is posing to us that we haven't yet had a chance to answer. And then finally, when you write down the Lagrangian for the standard model, you find that you can write down about 20 different terms that are all invariant. And each of those terms has an arbitrary real number in front of it. That's not determined by the symmetry arguments we've given so far, but is physically important. And all we can do is measure at the moment what those numbers are. So there's 20 something, 20, and 20, roughly 20 free parameters in the standard model. Why do they have the values they do? We currently measure those values, but we don't have any fundamental explanation of why they have the values that they do. So those are the basic questions those are some of the basic questions that are unanswered, that are sort of pressing issues in the sort of fundamental law of nature puzzle at the moment, and that we'd like to try to make some progress on, and that we'll talk more about in the next 2 lectures. Any other questions? I was going to end there.
So any students, if anybody has any questions?
I apologize for running.
Oh, I'm sorry.
Go ahead.
So, one is, you said that we know the form of these gauge groups via experiment. And my question is, how exactly would experimental results indicate what sort of symmetry? As in, how do we make that interpretation from experiments? And my second question, I'll just state quickly, is Yang-Mills, you said that the SM is a specific Yang-Mills theory. Now, the existence of Yang-Mills theories in general, is that just mathematical, or are there other Yang-Mills theories that have relevance in physics?
Yeah, so those are both good questions. Let me answer the second one first, because it's easier. So yes, Yang-Mills theories end up appearing in other physical systems. So there are a lot of, in condensed matter physics, even if the microscopic description of a system might be in terms of atoms and in a lattice and their interactions and how they interact with the electrons rattling around in the lattice. When you look at when you kind of blur your vision and look at the long wavelength properties of those condensed matter systems, in other words, when you look at them in the IR, usually they are described by a quantum field theory, and often that quantum field theory is a Yang-Mills theory. So you do actually get a chance to use some of these other Yang-Mills theories in those contexts. And then also, so those are often, those theories still live in either 3+1 dimensions, three spatial dimensions and 1 time dimension, or sometimes in 2 spatial dimensions and 1 time dimension, because sometimes there are condensed matter systems that are effectively 2+1 dimensional. They're confined to let's say like the quantum Hall system is effectively 2-dimensional because it's confined to essentially a single layer in the 3rd dimension at the boundary between two semiconductors. Anyway, and then higher dimensional Yang-Mills theories and other Yang-Mills theories also, may be important in physics, and we just see the low energy that the standard model we see may just be the low energy manifestation of a bigger Yang-Mills theory with a larger symmetry group and possibly more particles or possibly fewer particles. And so some of the ideas about grand unification make this very concrete. And so that'll have a chance to mention more next time. And there are also a number of ideas, famously string theory. Well, anyway, So yes, to make a long story short, other Yang-Mills theories do come up in other contexts, both as speculations, but then also in condensed matter as in real physical systems. In terms of the other question about how you experimentally determined that these were the right gauge groups, that is a very fascinating and long story. You know, I can only kind of give the highlights of that. I mean, I can only give a few indications about that, but you know, a huge breakthrough took place in the 1950s and 60s by Murray Gell-Mann, who began to going back even further, in the early days of quantum mechanics, back in the 1930s, I think, Heisenberg had the brilliant idea that maybe the neutron and proton were not just different particles, maybe they were just two manifestations of the same particle, and that you should kind of think of them as being grouped into a two-component vector that is rotated, and that they can kind of get mixed up into one another by the group SU2 acting as an internal symmetry, so what he called isospin symmetry. And so that was the starting idea, and by itself, that was the sort of beginning of the idea of these internal symmetries mixing particles that have nothing to do with space-time symmetries. But that by itself didn't explain too much, but then there was this huge breakthrough due to Gell-Mann, the so-called eightfold way, where he began to realize that particles were grouped into different representations, that they were discovering tons of new elementary particles left and right in the 1950s and 60s, and no one could make any sense of it, and there was just seemed like a giant mess. And then Gell-Mann realized that if you grouped them appropriately according to spin and according to charge, that they began to fall into representations of SU3. So that was the first indication that there was one of these bigger internal symmetry groups lurking in the structure of the standard model. Now that SU3 turned out to not be the same as this SU3 that ultimately appears in the standard model. That was a different SU3 that we would now call SU. Well, anyway, that's but in order to explain his SU3 patterns, he ended up realizing that the particles that we were observing, the so-called baryons and mesons that actually were observed by colliders, had to consist of smaller particles with only fractional charges, which are these quarks. So that was how quarks were discovered, which are these quarks that appear in the upper three rows of my table. And then once Gell-Mann had this huge success, people had the idea that it really drove home the idea that grouping particles into representations of different symmetry groups had something right about it. And so people began to play with a lot of different symmetry groups and representations, and in an attempt to find ones that described the data better and worse. So famously, Weinberg and Glashow and Salam figured out in a series of papers in the 60s, and I guess in the 60s, that SU2 and U1 seemed to do a good, that by grouping the particles into SU2 and U1 and adding a Higgs field that you could explain. It's kind of a long story. It's too long a story, really. And then another important breakthrough was that the way SU3, this SU3 gauge group was discovered, an important ingredient in that story was the understanding by Atuf and others that SU3 and Wilczek and Politzer and Gross, that SU3 was so-called asymptotically free. That if you scatter particles with higher and higher energies, that the so-called strong force due to this SU3 gauge group actually gets weaker and weaker at higher and higher energies, and that matched experiments that were being done. The way in which it got weaker matched very well with experiments that were being done at the time at the SLAC particle collider that were doing exactly that, colliding particles at higher and higher energies and looking at how they scattered off of one another. But yeah, it's a very complicated but fascinating, amazing story. Really, it's one of the greatest stories in human history for my money. But part of that is that it's hard to summarize quickly. But those are a few of the ingredients.
Thank you, sir.
But you
really
know now, but I mean, maybe speaking more abstractly and less historically, if you just try different, you could just try to kind of enumerate your way through the different Yang-Mills theories and write down for each theory, for each set of gauge groups and for each collection of particles, you could write down the corresponding Lagrangian, and then you could work out, okay, what are the basic particles in these theories? What are their masses? And when I scatter them off of one another in a collider, if I scatter a particle of type X and a particle of type Y, what particles can I get out at the end, and with what probabilities? And then you can abstractly speaking, what you're doing is you're taking those predictions and you're comparing them with what you see at actual colliders when you actually collide all the particles that you can together and see what comes out. And the point is just that for most Yang-Mills theories, the predictions have nothing to do with what you see. And then for this particular one, the predictions are absolutely bang on, So that's it, I guess.
Okay, Sumit Bishar, do you have any question?
Yes, Professor. I have a question. Professor, you didn't say anything about how the gauge field.
Biswajit? Oh, sorry. Go ahead.
Yeah, no, Mr. Sumit Bishar wants to ask you some question.
Oh yes, if you could mute your mic, Biswajit, it's a little.
Yeah.
Thank you.
Professor, you didn't say anything about how the gauge fields transform under which representation? I mean, G mu, W mu, B mu.
Yes, that's a good point. So if we go back here,
I mean,
let's see.
probably they follow the adjoint representation, right?
Exactly. So well, more correctly, if you look at the transformation law here, if this second term had been absent, then you would say that this is nothing but the adjoint representation of the gauge group. And so, or in other words, if you just look at how the field transforms under a space-time independent gauge transformation, then it transforms as the adjoint representation. But then this extra term means that it transforms. That A mu by itself doesn't really transform clearly, but F mu nu, the corresponding field strength does transform under the adjoint representation. And so in particular, G mu, the gauge field for the strong the strong force transforms with the SU3 gauge group here, whereas for G mu nu transforms on with a factor of SU3 on each side. Yeah, I didn't discuss the case where I didn't get a chance to discuss the more complicated case where the gauge group has multiple components, like in the standard model. But you can show that it works like this. That so if an element of SU3 times SU2 times U1 is written as, if you write an element of that as the triplet U3, U2, U1, so this is where U3 is an element of SU3, U2 is an element of SU2, and U1 is an element of U1, then the three different types of gauge fields transform in the adjoint, but with the corresponding group element U1, U2, or U3 as appropriate.
Okay. I had another question. Can I ask?
Sure.
The gauge invariance fact of the Lagrangian, I am imposing it, right? The parameter is space dependent, and I want my Lagrangian to be gauge invariant, so the gauge fields pops up, right? And the other terms of the Lagrangian, I am trying to do them as the gauge invariant term. And for this fact, I do that mu term is absent in my Lagrangian. So I say the fact that, for that reason, photon is massless because there is no mu term, there is no mass term. But in the first case, I am imposing the gauge invariant fact. How can I say that for this reason something doesn't have mass, because I want this to be gauge invariant Lagrangian? I mean, what happens if the Lagrangian is not gauge invariant or something like that?
Yeah, well, so I mean it's a philosophical question in a sense. I mean, it appears to be that the after fishing through different rules of the game to see which ones give a correct Lagrangian which describes the laws of nature, that gauge invariance appears to be the right requirement. By assuming that the Lagrangian has to be gauge invariant, we are restricted to a Lagrangian which matches observations. And if we don't assume that, we don't know how to get a Lagrangian which matches observations. So observationally, it seems to be, observations have told us that that's the principle to impose. And also mathematically, it just reflects the fact that, I mean, but in principle, the laws of nature could have been different. They could have not been gauge invariant, and so I think the physicist's answer is that it came observationally. Now, however, it has a geometrical meaning, saying that the Lagrangian is gauge invariant is a statement about what the underlying geometry of nature is. It's very analogous to in general relativity. I don't know if you've studied general relativity, but there you require that the Lagrangian is invariant under diffeomorphisms, or in other words, invariant under
parallel transformation. I get the fact the covariant derivative also pops out there in general relativity.
Yes.
And the curvature.
Yes, exactly. So it's very.
H mu is associated with the curvature, and
exactly.
So like that.
Exactly. And so in the general relativity context, it is saying that the fact that the Lagrangian is gauge invariant is reflecting a physical fact, which Einstein would have phrased as saying that the observer's coordinates are not physical, that the choice of reference frame in order to describe the physics is an arbitrary choice.
So Boyle got disconnected.
Yes, Professor. We left the meeting.
Sorry about that. Can you hear me?
Yes.
Yes, Professor.
Okay, sorry.
I can hear
my
you.
iPad just abruptly locked me out for some reason. Sorry about that. So let's see. I think I lost. Oh yeah. So in GR, the fact that the Lagrangian doesn't depend on diffeomorphisms reflects this physical fact that reflects the physical requirement that we're working in the framework of Riemannian geometry, so that the only so that we're free to describe tensors in a given coordinate system, but which coordinate system we use is completely arbitrary. And so similarly in Yang-Mills theory, the fact that the Lagrangian is invariant under gauge transformations ultimately is reflecting the physical statement that there is a vector space of fields living over each point in space-time, and you can to some extent, what basis you choose to describe the fields in that vector space is arbitrary. So it's not that yeah.
Hi, I'd like to add to what Latham just said, which is one can also look at one of the most successful gauge theories, which is quantum electrodynamics. And we can try to understand where gauge symmetry plays a role in the success, if you like, of QED. If one looks back at Maxwell's formulation of electrodynamics, then there is no hint there of the gauge principle, if you like. Maxwell writes down the dynamical equations of motion for electrodynamics in terms of the electric field, magnetic field, and charges or charge densities and current densities. And if you, for example, look in your favorite classical electrodynamics textbook, whichever it is, Jackson or Griffiths, you don't need, there is no reference to gauge symmetry for any practical calculation. So it seems to me that gauge symmetry becomes important as soon as you add quantum to electrodynamics, when you recognize that there is the possibility of making changing the wave function of the electron by a phase. You can now make this phase dependent on space-time. So in some sense, if you like, the quantum nature of it's when you move into the quantum domain that gauge symmetry becomes unavoidable, if I can use that word. Of course, there are examples even in classical electrodynamics, like I don't really know too many. Actually, I take that back. I don't know too many examples where you need to use gauge symmetry to explain classical phenomena. But I think it's essentially when quantum comes into the game that you need that gauge symmetry comes into its own.
That's a very good point. Very interesting point. About the classical case, though, what would you say about GR? I mean, there it seems that, well, I guess in principle you could formulate it in a way that
Yeah, I mean, if you look at the early successes of GR, like the precession of perihelion of Mercury or the bending of light, I mean, there is a gauge symmetry, there is a diffeomorphism symmetry, of course, but it plays, I mean, if at all it plays any role in the calculation, it is sort of, sort of a very marginal role, I would say. Would you agree with that, Latham? Would you agree that it plays a marginal role in at least in the early classical successes of relativity, general relativity?
to some extent, yes. I guess I would. I'm not sure how. I'm not sure how they. I think for both Einstein and Hilbert, I think the way they found their way to the theory was that the coordinate invariance was an important role
Yes.
in getting the right theory. I'm not sure how you would get to it without that.
Oh no, that's true that you would not be able to. But I mean, when you look at the experiment, Einstein's Gedanken of falling elevators, whether it's in free space or whether it is in an elevator falling in the field of in the gravitational field produced by a body. The key principle that Einstein has used there, the power of the argument, Einstein's argument, leads you to the equivalence principle, I would say, rather than diffeomorphism invariance, which is a mathematical, which is what appears on the mathematical side. On the physics side, the key tour de force of Einstein is the imposition of the equivalence principle.
Yes,
You're right. The discovery of the equivalence principle. And also, I mean, since you said Einstein and Hilbert, I mean, it's true that they more or less discovered the action very short, I mean, more or less independently and within a short time. But the arguments that Einstein uses to arrive, the physical arguments like the equivalence principle that Einstein uses, are far more powerful in terms of explaining how nature behaves. Rather than sitting down and just writing down all the curvature invariants and looking at just stringing together the ones that have the least number of derivatives and keeping those as I mean, I do not mean to.
I think that's a fair point. I think that's a fair point.
I'm not trying to undermine Hilbert's contribution, but fundamentally, Hilbert's idea is that just of a gradient expansion. But for Einstein to put together the physical argument about which comes from equivalence principle, that I think is the hallmark of a truly deep thinker.
Right.
Physics thinker, I would say. So again, to come back to this issue of gauge symmetry, or I think that diffeomorphism symmetry plays less of a role in Einstein's arguments. It's more, I would say, the equivalence principle. At the time that Einstein was studying this question, I mean, we cannot, of course, guess what he was thinking, but one might safely say that he wasn't thinking about the quantum theory of gravity. He was just thinking about classical geometrodynamics.
Yes. Definitely, though, one thing that he was thinking about, I mean, diffeomorphisms maybe he wouldn't have thought of it maybe in those the terms, but I think a thing that he definitely was thinking about was that the equivalence principle meant different observers in different reference frames should ultimately be describing the same physics, and so that the theory should be covariant under changes of coordinates representing the change between their different reference frames.
That is somewhat of a weaker statement, I would say, than diffeomorphism, than what we now understand.
That's true. Less global or something.
Yeah, I mean, diffeomorphism invariance now, it means a lot more, and now we know that the diffeomorphism group, it has it's very subtle. It has complicated homotopies then they, which then itself manifests in subtle ways when you write down wave functions, so on. Exactly in the same sense that Aharonov-Bohm effect comes into its own. Only in a semi-classical or perhaps even the quantum theory of QED. So I think that so in that sense I would say that gauge symmetry comes into its own only in the domain that quantum effects become important. I mean, these are just thoughts. I haven't really thought about this.
Yes, thought-provoking. Thought-provoking.
Except in the context of this particular question, which came about 5 minutes ago. Sorry, please go on.
Oh no! I think I'm done. Thanks for those comments. All right. Well, it sounds like maybe there are no more questions.
Yeah, I think there is one more question, I think. So, maybe you can stop here now if you want to say something.
I don't know whether I'm having trouble hearing you now for some reason.
Yeah. So I think there is some source of noise in Professor Chakraborty's microphone. So I'm very sorry that we are going. I mean, sometimes we are muting him because we don't hear anything else. So I thank you, Professor Boyle, for such a lucid explanation of these basic things, how this symmetry groups are coming in and how they are. We'd like to hear more about why you think that nature chooses this particular symmetry group. And for today, if there is no other question, we can stop here because you have already spoken for such a long time. You must be tired.
Yes, and, I apologize for running over.
Yeah, it's a throat, at least something hot. So we can stop here today if the participants doesn't have any more question right at this point of time, and we can come back tomorrow. I think not tomorrow. Sorry, tomorrow is Sunday. We are meeting again on Monday.
Okay.
I actually have a small thing to say regarding the gauge theory that I don't exactly remember where I heard this, but I think I heard that gauge symmetry somehow is related to locality and unitarity of a quantum theory. I'm not sure about it. I heard from someone saying that it's a quantum theory may violate locality if it's not local gauge invariant, but I'm not sure about it.
So yeah, I think that's true. That you can phrase it in different ways, but to write down a field theory that's local, unitary, and Lorentz invariant, that seems hard to do, or maybe impossible to do without without paying the price of introducing gauge redundancy. That in some sense, that's the gauge field is the cost of that.
No, I think I think one needs to understand this question a little bit more. One needs to put a little bit more structure into this question. There are models which are perfectly unitary and local and Lorentz invariant. The simplest models you can think of is the 5-4 theory or the Yukawa theory. There's no problem with this. But very quickly you realize that these are just models that you have made up in your own head, in the sense that they have a very limited application to the world that we see around us. If you want to describe the things that are happening around you, you cannot work with 5-4 theory, and you can't work with the Yukawa theory, except for a very limited class of phenomena. If you want to if we want to start investigating other interesting phenomena, especially at higher energies, then we need to go beyond 5-4 theory or Yukawa theory. Now, so I bring this up only to point out that locality, unitarity, and Poincare invariance do not impose gauge symmetry on you.
That's a very good point. I think that so I'm not an expert on this topic, but I think I think there's been a sort of, so I think I forgot an important point, which is that what spin of particle you're trying to describe. As the spin goes up, the more gauge symmetry enters the game. So if you want to describe spin 1 particles, then I think that the statement is that you need gauge symmetry, whereas for spin 0, like you say, I don't think you do.
That's right. So if you want to work with a spin 1 particle, which in nature, our favorite spin 1 particle is a photon, the first thing you need to notice about the photon is that it has no mass. So we need to make a theory that describes a spin 1 particle with 0 mass, which is Poincare invariant. This is remarkably difficult if we don't want to introduce gauge symmetry. And then you sort of you go back to the drawing board, write down Lagrangians or Hamiltonians that have gauge symmetry. You know that nothing can travel faster than the speed of light, so you need locality and Poincare symmetry, and so on. But in some sense, when you have gone back to the drawing board, you have admitted new beasts into the game, which you have admitted new players into the game, which is a local gauge symmetry. And so again, I mean, I just wanted to say that there's no logical inconsistency between a Poincare invariant local relativistic theory, which has no gauge invariant, which has no smell and sight of gauge symmetry.
Yeah,
it's just that these theories might be boring because they may have nothing to do with nature.
Right. I think there's also some examples of cases known of exact dualities where a theory that does have gauge symmetry is dual to a theory that has none. So I kind of agree with you that gauge symmetry seems, it's a redundancy. So it kind of suggests that maybe there's a more elegant, conceivably there might be a more elegant way to describe things that doesn't have the gauge symmetry. But for the case of the standard model, I think there's no other known way of doing it. There may be some way in principle.
Yeah, no, you're absolutely right. It just seems that introducing the gauge symmetry is the simplest way we can explain phenomena that occur in high energy physics.
Right.
Whether there exists another description which is local, relativistic, and causal, but does not require gauge symmetry, we do not know. At this moment, this particular way of modeling nature has worked extremely well. This is how I would put it. And beautiful. It's both beautiful and has worked extremely well.
Okay. So now maybe I.
Yeah.
Stop now.
Okay. Thank you very much. See you on Monday.
See you.
Yeah, see you on Monday. I wish a very good weekend to all of you.
Me too. Bye.
Bye.